It was generally assumed by most physicists prior to the 1920s and 30s that the universe was eternal and therefore self-existent, that it had always been here and really didn't require an explanation. There was one physicist said, Robert Dicke of Princeton University said, an infinitely old universe would relieve us of the necessity of explaining the origin of the universe at any finite time in the past. And up till about the 1920s and 30s, most physicists and cosmologists simply assumed that the universe had been infinite in time and therefore required no explanation. It was the ultimate explainer. The universe is eternal, it's self-existent, it's always been here, and therefore we don't need to give an account of where it came from. Well, there was a surprising discovery made in 1912 by an American astronomer named Vesto Slipher. And he discovered that the what were called nebula at the time were issuing light that was redder than it would otherwise look. It had a longer wavelength than would be expected. And that suggested that these nebular structures in the night sky were moving away from us in every direction. Now, at the time, astronomers didn't know whether the nebula were within our galaxy or whether they were beyond our galaxy. But by the 1920s, that issue had been settled, and it became clear that these nebula were actually other galaxies beyond the Milky Way, that the Milky Way was just one of, well, what we now know are hundreds of billions of galaxies. And so by the 1920s, Edwin Hubble, who was also studying this evidence called the red shift, the shift of the light coming from those different galaxies. It was stretched out in the red direction of the electromagnetic spectrum. So if you shine light through a prism, the light will separate it from red to violet. You get all the colors in between. The red light corresponds to the longer wavelength light. So if something is receding or moving away, the light from it will be stretched out and will look redder than it would otherwise look. It's shifted in the spectral lines. And Hubble discovered this red shift all over again, but now realized that the light was coming not from nebular structures within the galaxy, but from galaxies beyond our own. And that suggested that the universe was in every direction of the night sky, every direction where they could verify this red shifted light, that it was expanding. The amazing thing about the expansion of the universe is that it suggests that in the forward direction of time, the universe will be getting bigger and bigger and bigger and bigger. But if you wind that clock backwards in your mind and back extrapolate, as the scientists say, then you realize that the galaxies, which are now moving away from us, would at every successive point in the remote past have been closer and closer and closer together. Sometimes this is illustrated by blowing up a balloon. The universe is like a balloon blowing up now in the forward direction of time. But if you back it up in your mind's eye to think, where were all those galaxies in the past? At every successive point in the past, they were closer and closer and closer and closer together, till finally they would have converged in the past at some point, marking the beginning of the expansion of the universe. And arguably, the beginning of the universe itself. And so that became known as the idea of the Big Bang, the place at which the universe began to exist and began to expand outward in the way that we can now observe. Einstein's theory of general relativity played a very important role in the discovery of the beginning of the universe. Einstein's theory of general relativity was a theory of gravity. And his idea was that matter actually curves or warps space, or what he called space-time. Such an illustration would be like putting a big bowling ball on a trampoline, and the trampoline would then become depressed at the middle, and then and become warped overall. Now, if that theory was correct, then that implied that the universe was dynamic, that matter would be actively moving or changing the shape of space and space-time. So if the universe is dynamic and matter is pulling space in, then if gravity is the only force in the universe, then we would have to have a gravitational collapse, and then all matter would be congealed, all matter, space-time would be collapsed into a kind of a black hole. But Einstein realized that we don't live in that kind of universe. We don't live in a black hole universe where everything has been compressed into one big clump. Instead, there's open space between galaxies. And therefore, there must be some countervening force pushing outward in contrast to gravity. And he called that force the cosmological constant. And his theory, therefore, implied that the universe was dynamic and that something had caused the universe to expand. But what Einstein did was he chose a value for the cosmological constant that exactly matched the inward pull of gravity. So the outward expansion of the cosmological constant was contrived to exactly match the inward pull of gravity, so that rather than portray the universe as dynamic and likely expanding, as his theory would do on its face, he instead chose a value for this outward push, the cosmological constant describing the outward push, at exactly the right amount so that it would match the inward pull. And that allowed him to portray the universe as static, with neither a beginning nor an end. And for Einstein, this was a kind of philosophical relief, because he really didn't want at that point in his career to think about the beginning of the universe, because he didn't want to think about what would be necessary to explain the origin of the universe if we're talking about all of matter, all of energy, all of space and time. And so the cosmological constant, his fiddling with that value, allowed him to portray the universe as static and not expanding. Yeah, at the beginning of the 20th century and through most of the 19th century, it was just presupposed among most physicists and astronomers, cosmologists, that the universe was eternal in extent, that it had been here for an infinitely long time, and that probably it was of infinite spatial extension as well. So the assumption was that the universe was eternal, self-existent, self-organizing, but it did not have a beginning point which would have required an explanation for the origin of the universe. The origin of the universe had always been here. Yeah, it wasn't just Einstein who didn't like the idea of the universe having a beginning. Other physicists and astronomers, astrophysicists, had a kind of emotional reaction against it. Even Sir Arthur Eddington, the great British astrophysicist who brought Einstein into the picture as far as the evidence of the redshift in the expanding universe. Eddington invited Einstein to Cambridge in 1929, and they had a famous conversation where Einstein told him about the work of Hubble and Humason in California, establishing that the universe was expanding. But Eddington himself didn't like the idea. He said, philosophically, the notion of a beginning to the present order is repugnant to me. He said, I should like to find a genuine loophole. The idea of the Big Bang, he said, is preposterous. It leaves me cold. So he was aware of the evidence, presented it to Einstein, but then himself expressed this kind of emotional disdain for the idea. And later, a physicist, Robert Dicke at Princeton University, explained what was going on in the minds of many physicists. He said that an infinitely old universe would relieve us of the necessity of explaining the origin of the universe at any finite time in the past. By contrast, if the universe has a definite beginning, then you have to think about what caused the universe itself, the universe of matter, space, time, and energy to come into existence. Clearly, that's not going to be something that can be readily explained by matter, space, time, and energy, because those are the very things that come into existence. So providing a materialistic explanation for the origin of the universe becomes very difficult, because it's matter itself that begins to exist. Einstein was later forced to abandon the static universe idea for two reasons. First, his fiddling of the value of the cosmological constant seemed to a lot of physicists to be extremely contrived. The cosmological constant could have had a range of values, from very weak to very strong, but he chose exactly the value that would give it this static outcome. The problem with that is that implied an incredible degree of initial fine-tuning, which itself was kind of mysterious. And secondly, as physicists began to work with his equations of general relativity, they showed that even if the value of the cosmological constant had been fixed just right, even slight variations in the distribution of matter in the universe would throw off that balance, causing the universe either to rapidly expand or contract, that it was not going to be possible to maintain that static state. His theory implied a dynamic universe. But then secondly, as the evidence of the red shift became more and more widely known among physicists and astronomers and cosmologists, and the evidence for the actual astronomical evidence for an expanding universe became clear, it became obvious that Einstein's fiddling was contrary to what the evidence actually showed, that in effect the heavens talked back. And in 1927, on the way to a physics conference, Georges Lemaitre, the famous Belgian physicist, also a Catholic priest, had a now famous taxicab ride with Einstein, where he told him about the redshift evidence and also explained that he had solved Einstein's field equations and that they most naturally pointed to a dynamic expanding universe with a definite beginning. And so by the end of the 1930s, there was a convergence between theoretical physics, which was pointing to a beginning based on Einstein's theory, and the evidence from observational astronomy that was then confirmed by Hubble and his colleague Humason at Caltech. And there's some famous newsreel footage from 1931 where Einstein accepts an invitation from Hubble to come out to the Mount Wilson Observatory in Pasadena, California. And Einstein looks up through the camera and then comes out and discusses with the media that he now realizes that the universe couldn't be static, that there's evidence of a beginning. And he gives an interview with the New York Times a couple weeks later and says that Hubble and Humason had now convinced him that absolutely that the universe could not be static. It must be expanding. There must have been a beginning. Later he calls his fiddling with the cosmological constant the greatest blunder of my scientific career. So Einstein finally comes around, and so by the 1930s you get this convergence between observational astronomy on the one hand and theoretical physics on the other, both of which are now pointing decisively to the really unexpected conclusion that the universe must have had a beginning. Edwin Hubble was a lawyer who went into observational astronomy at a really propitious time. It was just as the astronomers were building these large dome telescopes. And Hubble had the opportunity to use the great 100-inch dome telescope at Mount Wilson. And he began to observe the night sky through this big telescope, which was able to resolve little tiny points of light with a much greater precision than smaller telescopes had done before. And secondly, at this time, astronomers started to use photographic plates that could collect light over long periods of time. And so these two advances, the bigger telescopes and the use of photographic plates, allowed them to get very high resolution images of little points of light in the night sky that previously had seemed quite indistinct, but now were revealing themselves to be spiral nebular structures. And through an interesting chain of reasoning, Hubble realized that these nebular structures were actually galaxies beyond the Milky Way. In the 1920s, there was still a debate about whether the Milky Way was the only galaxy or whether there were galaxies beyond it. But as techniques for measuring distances to remote objects in the night sky advanced, it became clear that many of these little points of light in the night sky were not nebular structures of amorphous gas within our galaxy, but were rather distinct galaxies way beyond our galaxy. And so the combination of these distance measurements, these abilities to measure great distances in the night sky, along with Hubble's observations through the big telescopes, enabled him to establish that there were galaxies beyond our own, and then further, that the light coming from those galaxies was being stretched out and was what astronomers call red-shifted, such that the best explanation for what was happening with these galaxies is that they were moving away, they were receding from us, and that suggested, in turn, that the universe was expanding from a kind of cosmic beginning point. One way to think about the expanding universe is to think of a balloon being blown up. If you draw some spiral structures on the surface of the balloon and then you puff, 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 blow the balloon up, that illustrates the way the universe is currently expanding. Every successive moment, it's getting bigger and bigger and bigger, and the galaxies are getting further and further away from each other. The galaxies on the edge of the universe, the galaxies in the middle, they're all getting further and further away. But now imagine what would happen if you back the time sequence up, if you back extrapolate. Then that can be illustrated by thinking of the balloon getting smaller and smaller and smaller, and corresponding to its size at every progressive point in the past. And at every progressive point in the past, the galaxies would be getting closer and closer and closer and closer together, till finally you reach a limiting point where all the galaxies congeal into one infinitely hot, dense point, marking the beginning of the expansion and arguably the beginning of the universe itself. Balloon collapses onto itself. Georges Lemaitre was a Belgian physicist who was a Catholic priest who in the 1920s first synthesized the evidence from observational astronomy concerning the expansion of the universe based on the redshift evidence, and the implications of Einstein's theory of general relativity, which implied a dynamic universe from expanding outward from a beginning point. And he showed that the physics and the astronomy were convergent, that they were giving the same testimony, and that really was the beginning of what's known as the Big Bang Theory, because he brought the two strains of evidence, the observational evidence and the theoretical physics, into one coherent synthesis. After the Big Bang Theory was established in the 1930s, there were a series of attempts to explain the expanding universe without implying that the universe had a beginning. And one of the most famous of those was postulated by Sir Fred Hoyle, the British astrophysicist, along with colleagues Hermann Bondi and Thomas Gold. And what they proposed was that, yes, the universe is expanding, but that as the universe expands, new matter is being created as the expansion goes. And so they posited kind of arbitrarily that the universe must exist in a state of constant density, so that however much space there is, there's a corresponding amount of matter so that there's always the same density. So what they suggested was that the universe was expanding outward, but as it stretched, then the density would start to decrease, and that would force matter to be created. And they said that there was a C field, a creation field, that was responsible for this matter popping into existence. And in so doing, what they suggested was that the universe had always been infinitely large. It had always existed. It had been here for an infinitely long time, and it was just getting more infinite. It was getting infinitely bigger, but it was infinite to start with and getting infinitely more big all the time. And so they still had an expanding universe, but one that was expanding outward for an infinite amount of time, having been infinitely large from the beginning, except that there was no beginning. The universe had always been here. So they kind of restored the idea of an infinite, self-existing universe, but in some way also explained or took account of the expanding universe. Then there was another theory that attempted to explain the expanding universe, but retain the idea of an infinitely old universe. And this was the idea of the oscillating universe. And the idea here was that the universe would be expanding outward, but then as the expansion slowed, the matter in the universe, by gravitational force, would cause the universe to recollapse. But once it recollapsed, then by some unknown mechanism, it would expand again. So you'd get a series of big crunches followed by big bounces, okay? And this was known as the oscillating universe. And that then could account for why the universe looks to be expanding now, i.e. we're in an expanding phase, but later there would be a contracting phase, and that would continue kind of like an accordion, in and out, in and out, in and out. That theory ran into two big problems. The first was it was discovered that there was not enough matter in the universe, even counting the dark matter, that physicists have to infer but can't observe, to cause the universe to recollapse. And secondly, it was determined by thermodynamic analysis. MIT physicist named Alan Guth showed that the energy available to do work would diminish with each successive cycle, that there'd be a buildup of entropy, and therefore less energy available to cause that outward push. So that even if there was an outward push, it would be smaller, and eventually each successive outward expansion would be smaller and smaller and smaller. It'd be kind of like a ball bouncing to the ground, and finally it would damp out to a nullifying equilibrium where there's no more bounces, okay? And now if the universe had been infinitely old, then that means we should have reached that nullifying equilibrium point long ago. But since we aren't in such a point, we can infer that the universe wasn't infinitely old, and there still must be a beginning. So even if there were a series of bounces, there must have been a beginning, was the conclusion. So the oscillating universe also, I think, ran into trouble, both for theoretical and observational reasons. And so the idea of the Big Bang really began to be accepted pretty widely by the 1970s and 80s. In the 1960s, there was another really interesting development in theoretical physics that added to support to the Big Bang theory. And that came with the solution of Einstein's field equations by Stephen Hawking, and then later by Roger Penrose and George Ellis, three great physicists, British physicists. Ellis was South African, but he was studying at Cambridge. And during Hawking's PhD years, he was studying black holes. And he began to think about black holes in relation to the origin of the universe. If general relativity is true, he thought, then if the universe is getting smaller and smaller and smaller in the reverse direction of time, then the matter of the universe would have been more and more tightly compressed. And as you go further back in time, the density of the matter in the universe gets higher and higher, but that would cause the curvature of the universe to get tighter and tighter. And he showed that as you go further back in time, as the matter gets more densely compacted, the curvature gets more tightly compressed, and you keep extending that backwards, you reach a limiting point where the curvature of the universe must go to an infinite. The matter gets infinitely tightly compressed, the curvature gets infinitely tight, and at that point, the laws of physics break down in what's called a singularity. And that singularity marks the beginning point of the universe. Now, there's a little film called The Theory of Everything, and in the film they depict in the film they depict Hawking's PhD examination, and the examiners are picking apart his other chapters. But when they get to this fourth chapter where he develops the case for the singularity theorem, one of his supervisors says, "A black hole at the beginning of the universe? That's brilliant, Stephen." And then they push the book across the table and say, "Congratulations, Dr. Hawking." And now, but then after that, Hawking avows that he's going to go work out the math in more detail, which he subsequently does with Roger Penrose, one of the PhD examiners, a great physicist from Oxford. And so Penrose and Hawking and another collaborator, later George Ellis, solve Einstein's field equations, and they do so not making some simplifying assumptions that LEMAITRE had made, but eliminating those simplifying assumptions and solving them with full rigor, thus showing that the implications of Einstein's theory are very definitely that the universe had a beginning, not only in time, but also in space, that there's a point where the curvature of space gets infinitely tight, corresponding to zero spatial volume. Now, you have to ask, that's a profound image, because if you think how much space can you put in, how much stuff can you put in zero space, the answer is obviously none. And so the singularity theorems have a kind of profoundly anti-materialistic implication, because they suggest, as Hawking and Ellis later put it, that this looks something like a creation event. And so that development in theoretical physics, along with the refutation of the oscillating universe and the steady state universe by the 1970s and 80s, establishes the Big Bang theory as the dominant theory among cosmologists and astrophysicists. Well, in 1965, Robert Wilson and Arno Penzias, two engineers at the Bell Labs in New Jersey, discovered some radiation that was thought to be the echo of the initial Big Bang. If the Big Bang theory were true, then after the beginning of the universe, there would be a point where all the matter and energy of the universe were congealed into a kind of infinitely hot, dense point. And that intense concentration of matter and energy would produce radiation that would then begin to radiate throughout the universe and eventually cool. And physicists have made calculations as to the temperature equivalent of that radiation. And physicists, including one at Princeton University nearby the Bell Labs, were looking for that radiation. Penzias and Wilson found it in 1965, and it confirmed a prediction of the Big Bang theory, one that was expected if the Big Bang were true, but not expected if the steady state were true. The steady state theory envisioned matter popping into existence in little pockets as the universe expands, and never imagined that all the matter and energy would have been condensed into an infinitely hot, dense point. Therefore, it didn't expect to have the radiation from that infinitely hot, dense point pervading the universe today. So when that radiation was discovered, it supported the Big Bang and disconfirmed a prediction of the steady state. And from that point forward, I think the steady state was pretty much rejected by most physicists. Even Hoyle and even Hermann Bondi, one of the initial proponents of the steady state, rejected the steady state theory. I was a grad student in Cambridge in my first year and was at a high table dinner sitting next to Bondi. And he told me the whole story. You know, he said the only thing wrong with our theory was that it was totally wrong. Oddly, Hoyle and Gold never repudiated it, but Bondi did. The most common attempt to get around the idea of a definite beginning to the universe is not coming any longer from any evidence from observational astronomy. It's coming from extremely abstract models in theoretical physics, one of which is called, the most significant of which is called quantum cosmology. If you think about the Hawking, Penrose, Ellis singularity theorems, they allow physicists to back extrapolate. They imagine what the universe would have been like as you back extrapolate, and that it would come to this infinitely tight curvature. But there is a tiny loophole that you can invoke to avoid that conclusion of a singularity. It happens that when the universe is incredibly small, when it's smaller than 10 to the minus 43rd of a centimeter, that it would be subject to what are called quantum effects or quantum fluctuations. And in that tiny little smidgen of space just after the universe would have begun, we're not sure how gravity would have worked. And so if we're back extrapolating to a beginning based on Einstein's theory of gravity, at that tiny point, there's a possibility that gravity might have worked entirely differently. And so some physicists have developed models of what are called quantum gravity or quantum cosmology. And what they do is they describe how the universe would have functioned, or they describe the universe using the mathematics of quantum physics. And that allows them to portray the universe as possibly coming into existence essentially from a set of mathematical possibilities, rather than from nothing physical. They can think of the laws of physics causing the universe to come into existence. Now, that's a very interesting kind of move philosophically, because rather than saying the universe had a material cause, or saying that the universe came into existence from nothing physical, which were the two previous options, now we have a kind of depiction of the origin of the universe where it's coming into existence as the result of a mathematical equation describing how the universe would function when it was extremely tiny. And if you, in quantum physics, there's something called the collapse of the wave function, where as a wave of light passes through a double slit in a famous experiment, it seems to be passing through as a wave, but then when it hits a detection plate, it collapses and has a specific particle-like manifestation. And in the same way, these equations applied to the origin of the universe depict the universe as having many possible gravitational fields and spatial geometries. The universe, it describes many possible universes. And then if our universe is one of the universes that's described by that set of possibilities in what's called the universal wave function, then the physicists think they've explained the origin of our universe. Our universe is described by the math of quantum physics. But there's a catch. It's very odd to say that the universe came out of math. And one of the proponents of this quantum cosmological idea, Alexander Velinsky, has asked himself in his own book a rhetorical question. He says, if the universe existed, if our universe first existed as a set of mathematically describable possibilities, as a mathematical expression, but math exists only in minds, are we then saying that the universe came out of a mind? And then he never actually returns to answer his own rhetorical question. Hawking tumbled to the same insight. He said, what puts fire in the equations that gives them a universe to describe? And now, in my own research, I've made a further discovery about this explaining the universe as a result of the universal wave function. And that is, to get a universal wave function, you have to solve a prior equation called the Wheeler-DeWitt equation. It's the analog to the famous Schrödinger equation in regular quantum mechanics. But it turns out that the Wheeler-DeWitt equation has an infinite number of solutions. It's technically known as a functional differential equation. And such equations cannot be solved unless the physicists themselves select what are called boundary constraints or boundary conditions. And those boundary conditions restrict the degrees of mathematical freedom associated with the equation. Now, in ordinary physics, boundary constraints are decided or determined by the physical system that's being described. But since there's no physical system being described by the Wheeler-DeWitt equation yet, because it's being used to explain the origin of all physics, the origin of the universe, the physicists have to choose the boundary constraints. And they choose those with an outcome in mind. They choose those in such a way to give a solution to that equation which would be a universal wave function, that would include a universe like ours. So they have a teleological, end-directed objective. And so they limit the degrees of mathematical freedom in the original equation. They get a function out that includes our universe as a possibility, and they say they've explained the origin of the universe. But what have they actually modeled? They've modeled the need for a mind to constrain degrees of mathematical freedom with this selection of boundary constraints. And in so doing, a mind that is inputting information into the equation in order to get an outcome that would include a universe like ours. So I think what they've actually modeled is a form of intelligent design. They've suggested that there would need to be a mind constraining the possibilities so as to get a universe like ours. And that quantum cosmological theory, whether it's true or not, has oddly, though it's being used to refute a God hypothesis and to say, well, the universe either didn't need a beginning or it can be explained from physics, literally from nothing by the laws of physics, actually implies the need for a pre-existing mind and a mind that would constrain possibilities, input information in order to get a universe like ours. Well, the Big Bang Theory, coupled with developments in theoretical physics, suggests that the universe has been expanding from a finite beginning point, where not only matter and energy, but time and space itself began. In Einstein's physics, time and space are connected. And as space becomes more tightly curved, as Hawking showed, as you go further back, and it eventually reaches a limiting point of infinitely tight curvature. And as time reaches a beginning point, before that, no physical reasoning is possible because there's no physics before that. That's where physics begins. The laws of physics break down at that point. So to explain the origin of the universe, literally the origin of matter, space, time, and energy, at a finite point in the past, it becomes implausible to invoke matter, space, time, and energy. If you're trying to explain the origin of matter, you can't posit a materialistic explanation because there's no matter there before the beginning to do the causing. So if the universe does have a beginning, and by the principle of causality, all events that begin must have a cause, we then must look for a cause that is immaterial, that transcends matter, space, time, and energy. And that's where I think theism, or something like it, perhaps deism, has a great deal to offer, because those metaphysical systems of thought posit an immaterial entity of great power that could bring the physical universe into existence. There's a method of reasoning in the philosophy of science, a method of reasoning in science called inference to the best explanation, where scientists posit that entity which, if real or existent, would best explain the evidence. Well, if you use that method, the entity which, if real or existence, that would best explain the evidence, would be an entity that transcends matter, space, time, and energy, and can act to initiate new events. That sounds an awful lot like a mind, a transcendent mind. And so the transcendent mind posited by theism, or perhaps deism, I think better explains the origin of the universe than any materialistic explanation, again, for the simple reason that materialism can't possibly succeed because there's no matter prior to the Big Bang that could explain the origin of the material universe. There's another development in theoretical physics called the Born-Guth-Vilenkin theorem. And it's not based on general relativity, but it's based on special relativity. And for that reason, it is not affected by postulations about what gravity might or might not have been like within the first tiny smidgen of time after the beginning of the universe. And it's those speculations that prevented the Hawking, Penrose, Ellis singularity theorems from absolutely proving a beginning point. Instead, the Born-Guth-Vilenkin theorem proves a beginning to the universe, but on the basis of considerations from special relativity that have nothing to do with whether or not there were quantum fluctuations within the first tiny smidgen of time after the beginning of the universe, and whether gravity might have worked differently or not. Instead, it's independent of all those kind of considerations and caveats that prevent us from saying that the Hawking, Penrose, Ellis results are absolute proofs. Instead, you have a very strong proof of a beginning from theoretical physics that is not dependent on these conditions. And so that's another line of evidence suggesting that the universe had a beginning. In fact, it applies to all cosmological models, whether inflationary or otherwise. And so physicists can say, well, maybe the universe just was always here. But the evidence from observational astronomy is pointing to a beginning. I would argue that the singularity theorems of Hawking and Penrose and Ellis at least point strongly to a beginning. But then in addition to that, I think you have a very considerable and compelling proof of a beginning based on special relativity that's been advanced by Born-Guth and Vilenkin. And so those three lines of evidence and/or developments in theoretical physics, I think, converge on a very compelling conclusion. As best we can tell, the universe had a beginning. Some have wanted to say that our universe is just one bubble among countless others, among an eternally inflating universe. That's a consequence of something known as eternal chaotic inflation. It's a new cosmological model. But the Born-Guth-Vilenkin theorem showed that on the basis of special relativity, all models of the origin of the universe which imply an expansion, and the eternal chaotic universe has an expanding so-called inflaton field, that all such models must terminate eventually with a beginning. So the eternal chaotic inflation model does not circumvent the implications of the Born-Guth-Vilenkin theorem. It too must have started from, if true, it too must have started from a beginning. Some cosmologists will claim that older models, like the steady state and the oscillating universe, are making comebacks. But this appears mainly to be a form of metaphysical desperation. The evidence from multiple lines of evidence and several separate theoretical developments point strongly to the beginning of the universe. And the attempt to resuscitate these older models seems more to be a consequence of a distaste for their implications, for the implications of the Big Bang, than it does from any significant new developments in physics that would justify those models or reviving them. For example, there's a new model of the oscillating universe that suggests that the universe expanded and contracted and expanded and contracted, and that there's a new generation of entropy or low entropy with each cycle. But the models, the physicists who propose this don't actually explain where that new energy available to do work would come from. They just posit that it happened. So I think there's a bit of desperation in these attempts to circumvent the idea of a beginning. Lawrence Krauss claims that he can explain the universe from nothing on the basis of quantum physics, and that these models do not require any external control. Oddly, what I've shown in my new book, Return of the God Hypothesis, is that Krauss's nothing involves the equations of quantum physics. And insofar as equations are mathematical entities, and insofar as mathematical entities are abstract concepts, what we know about the existence of abstract concepts is that they always exist in minds. So his nothing seems to imply the need for a pre-existing mind. But secondly, the mathematical expression called the universal wave function that he invokes to explain the origin of the universe. After all, he's popularizing the model of Alexander Vilenkin, who uses a universal wave function to explain the origin of the universe. That universal wave function is actually the consequence of the physicists solving a prior equation called the Wheeler-DeWitt equation. And they can only solve that equation because it has an infinite number of solutions if they exert control on the equation in the form of what are called boundary constraints. What they do is they limit the degrees of mathematical freedom associated with that equation to get a universal wave function out that includes a universe like ours. But that is actually modeling a teleological end-directed process. In other words, intelligent design. How does the equation get constrained so that it can be solved to produce a wave function that will describe a universe like ours? It gets solved by the physicist choosing specific constraints or controls or conditions to impose on the equation to get the outcome that the physicist wants. And so Krauss is exactly wrong. The universe doesn't come from nothing in his model. It comes from math, but the math is only explanatory if prior math is constrained by the physicist to get the answer the physicist wants. And that, I think, is modeling the need for an input of information to constrain degrees of mathematical freedom by a mind. And therefore, I think even if Krauss's model and Vilenkin's model of the origin of the universe is correct, they're quantum cosmological models, that what those models actually imply is the need for pre-existing mind and pre-existing inputs of information into a set of mathematical possibilities to constrain those possibilities to get the universe that they desire. Yeah, Sean Carroll has questioned the idea that the universe has a beginning on the grounds that general relativity does not apply or may not apply in the first tiny smidgens of time when the universe would have been infinitesimally small. I've argued that what we know from general relativity, the singularity theorems, at least point to a beginning. But I've also pointed out that if these quantum mechanical-based models of the origin of the universe are true, and we don't apply general relativity to our understanding of the very beginning of the universe, that those models also imply a beginning. The singularity is not removed in quantum cosmological models. It's presupposed. But secondly, that those quantum cosmological models have, for other and additional reasons, theistic and immaterialistic implications. They suggest that the universe arose from a purely mathematical state, and they arose as the result of a mathematical equation somehow being constrained to produce a particular state that includes a universe like ours. And in the modeling, the constraints on that mathematical equation, called the Wheeler-DeWitt equation, are always supplied by the physicists who choose the outcome they want in order to get a mathematical expression that includes a universe like ours, which they then say explains the origin of the universe. It's a very odd thing to explain how matter can come out of math. But that's what these new models are essentially saying. And if that's what they're saying, they have theistic implications every bit as compelling as the evidence for a beginning.